All right. So today what we're going to do is we're going to talk about some periodic trends. This is kind of, there's one more little section of content in this unit, but for the most part, it's about exploring some of these activities and looking at different things. For the people that were in class on Monday, we colored in a periodic table with the different groups, outlined the metals, the metalloids, and the non-metals. If you need to review that, the PowerPoint is in here. Some of you actually might have missed that. I might make a video for that. I'll talk to the three of you that were gone and see what you need me to do for that one. I don't remember how much we covered when everybody was in class and how much was after. But today we're going to talk about these 5 periodic trends. The last one, honestly, will be pretty quick. It's a pretty simple one, but we're going to talk about these 5 trends. We're going to talk about why they exist the way they exist and how we can see them on a periodic table. I'm going to go a little bit fast in this video just so that we can get through it and you guys can watch it at your own pace. If you're going to take notes, you can obviously either slow it down, make me sound really dumb as I talk slowly, or just pause the video when you need to. Make sure you get the notes. The PowerPoint is already in the Google Classroom, so that part should not be an issue. So the major trends that we're going to be looking at are electronegativity, reactivity, atomic radius, initial ionization energy, and atomic mass. We've already talked a little bit about 2 of these and kind of sort of a third. We talked about atomic radius and initial ionization energy when we were doing our electrons unit. And then we talked a little bit about atomic mass just as part of isotopes and the periodic table in general. But we'll talk about both of these things going forward. So electronegativity. First of all, we have to know what electronegativity is. And electronegativity is the tendency for an element to gain an electron. So things that really want to bring electrons to them are very electronegative, and things that really don't like gaining electrons, they tend to push electrons away. They're very low in electronegativity. Now, just based on that information alone, you might be able to predict which group is expected to be the most electronegative. We talked in class about the different groups, and one group in particular tends to be very reactive because they really want to gain an electron. This has a lot to do with the valence electrons in a shell. So, for example, if I have an atom that has 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell, it really wants to get all the way over to 8. But it's missing 1. So it's going to pull in any electron it can find to try to complete its valence shell. And that's going to make it highly electronegative. Of course, the group of elements that have 7 valence electrons in their outer shell are the halogens. So hopefully we can figure out quickly that the halogens are the ones that are the most electronegative in general. So halogens only need 1 electron to fill their outer shell, so they tend to be the most electronegative. Now, another question is, would you expect heavier or lighter elements to be more electronegative? So if we think about like the top of the halogens, that's where we've got fluorine. It's got its 1s energy level here, and then it's kind of got its 2 energy level out here. If we go down a little bit further towards the bottom of the periodic table, we're getting to where we have all these different elements. So would an element like this or an element like this be more likely to pull in that last electron to fill its shell? And it's kind of an interesting question that might be a little bit hard to think about. But when you think more about how atoms are actually arranged, it starts to make a little bit more sense. So if we think about this, all of the positive charge is located right here, right? And then we've got a whole bunch of minuses, so 2 minuses there, and then 7 more minuses out here. Boom, like that. So this 1 electron has to kind of combat these minuses to try to get to this plus. Now, admittedly, the charge is much bigger in these bigger atoms. There's a much bigger positive charge here, but there's so much negative that's in the way, and it's so much further away from that center bit that this has a much stronger pull. So smaller elements, things closer to the top, tend to be more electronegative overall. So the reason we're kind of talking about those in little like parts is because we want to understand the why of this. I could easily just show you the trend and say electronegativity increases as you go this way, and it increases as you go this way. So basically, electronegativity increases like that. Ta-da, cool. But that's not particularly useful, right? Like you could look that up on Google, who cares? The important thing is to understand why that happens. Lithium is really low in electronegativity because it wants to get rid of electrons, not gain them. Fluorine is desperately trying to gain electrons as quickly as it can, and it's a really small element, so everything is close to the nucleus. So it's a lot easier for it to pull things in. It doesn't have as much blocking it out. Down here at, like, let's say iodine, we still want that last electron really badly, but because we have so much more stuff in the way, it's harder for a positively charged nucleus to attract electrons from the outside. Not to mention the radius of this element is just so much bigger. Iodine is, something like this, while fluorine is something like this. So if an electron coming by, it's really close to that center already. Whereas with this one, it's like, it's pretty far away from it, so it's a little bit harder to get pulled in. So again, electronegativity is increased as you get closer to the top right of the table. So it increases as you go left to right. It increases as you go up to down. And fluorine is the most electronegative element. Now, interestingly, elements like oxygen, for instance, very electronegative element, is probably more electronegative than iodine, even though iodine is in that halogen group. So it's not like a one-to-one necessarily, but in general, you're going to have stuff kind of more electronegative over here, and then we get kind of less electronegative over here, and then we get really not electronegative down here, and then these are kind of an intermediate. In general, the transition metals tend to not be particularly reactive either way, so we usually only look at these elements and these elements with electronegativity, and it's mostly for covalent bonds, which we'll get to later. So again, key points. Electronegativity is the tendency of an atom to gain an electron. It increases as you get closer to fluorine, basically. So up and right is increasing electronegativity. Next one, reactivity. We've already talked about reactivity a couple of different times within this class. Now, this is a really interesting graph. It's kind of hard to just picture it on a normal periodic table. Because you have different kinds of reactivity, right? The metals, that's these elements, and then basically everything down and left of here, tend to get more reactive as you go left and down. But when we kind of hit this middle bit right here, we get the nonmetals, and nonmetals are kind of in the opposite direction. Now, if we looked at a normal periodic table for reactivity, the way we've been talking about it, this is decreasing electronegativity towards the center. We hit that carbon group where it's really non-reactive, and then we get more increasing again out here. So if this red line represents increasing electronegativity, it kind of stops right here, where everything decreases, gets at its lowest. Now, obviously, again, there's like kind of a gap here, but that's okay. We don't really worry about that one too much. And then on this side, the smaller atoms are actually more reactive. On this side, the heavier atoms are more reactive, and has the same thing to do as with electronegativity, right? This one wants to pull in electrons as much as physically possible. Now, these all want to push electrons out, and if your electron is really, really close to the center, it's harder for it to get away than if it's in this really big atom where you've got like a bunch of energy levels. There's one extra electron that's trying to leave. It's a lot easier to leave this giant thing where your positive charge is way away from you than it is if you're really close to the center and there's only one or two other electrons pushing you out. So that's why the reactivity over here goes down, but the reactivity over here goes up. It's because of whether or not they're trying to lose or gain an electron. These are all trying to get rid of electrons. So losing electrons. These, on the other hand, are all trying to gain electrons. So you have the opposite in the trend, right? So that's why kind of towards the middle, like this spot right in here is going to be where you hit the lowest reactivity. But this group in general. And again, we don't count the noble gases here. Noble gases are incredibly non-reactive. They're a little bit of outliers because they already have that filled shell. So they are less reactive than the carbon group. But again, we don't really worry about those too much. So this graph is just talking about what I was just saying, except it's a little bit more color-coded. So you've got metal reactivity increases as you go left and down. Again, all of the elements over here are metals, all of the elements in here are metals, so this makes sense. Non-metal reactivity goes kind of up and right, and again, that's because these are pretty much all non-metals. So once you hit that carbon group, everything over here is an up and right one. Atomic radius, we have talked about this one a bit. Atomic radius increases as you get bigger because you have to add more energy levels. So you get to like francium down here, it has to have 7 energy levels. That's a lot of energy levels. I mean, even just drawing circles, that's going to get big. Obviously, electrons don't form in circles quite like that, but that is a bad idea when you're thinking about the size of them. It just has to get bigger because there's more energy levels. The atomic radius, however, decreases as you go this way, and this might be counterintuitive. We're thinking, okay, well, we're adding more protons as we go to the right, and we're adding more electrons, you would think it would get bigger. But actually what happens is, because that's on the same energy level, you just have more attraction between the center and these electrons. So they pull in closer. These opposite charges, the positives and the negatives, they attract each other. So this kind of brings the element in, or the atom in, as you go left to right. So atomic radius will decrease as you go this way, and it will increase as you go down. Which means in general, fluorine is again one of our smaller ones. Now that's not entirely true because hydrogen is of course the smallest. And then you kind of, again, have sort of a weird thing going on with the noble gases. So generally, we don't count them as part of this trend either. Now, initial ionization energy. This is the energy that it takes to remove an electron from an atom. It's basically it's similar to electronegativity in that it's the energy, it has to do with electrons, and it has to do with getting rid of them. The difference is that this one is kind of the idea of how easily an electron loses, or an atom loses an electron. So the easiest elements to remove an electron from are the alkaline ones. They already want to get rid of their only valence electron. They want to react so they get that full shell, so they're trying to push that last electron away anyway. The halogens, on the other hand, they really want to gain electrons, so it's really hard to get them to give one up. If you're one away from being, getting everything that you want, and somebody tries to take one of the ones you have, well, you're not going to like that. You're going to try to hold on to it as much as you can, and it's the same thing with the halogens. So in general, it's also easier to remove electrons from larger elements. Again, we have that positive charge in the middle. We get way out here, and it's like, yeah, this electron over here, it can get pushed away pretty easy, right? Some smaller element comes up and is like, hey, look at how cool I am. You should come over here. And it's just like, yeah, okay, you're a lot closer anyway. So that's kind of how that works. I feel like there's an America social studies joke in there, but I won't make it. So here's kind of the general trend in ionization energy. It increases as we go up, because again, ionization energy is the amount of energy it takes to remove. So the harder it is to remove, the more ionization energy it takes. So it's harder to remove an electron as we go up, and it's harder to remove an electron as we go to the right. So the element that's easiest to get an electron off of is francium. The element that's hardest is probably fluorine again. So again, this is a review one. We have talked about this before. This one shouldn't be too terrible, but it is important to know which way these trends go. And for people in class that have colored in their periodic table, we're going to be labeling it with these arrows and stuff. So you may want to do the same if you can print off a periodic table at home. Probably can't, but that's okay. You'll get one when we get back. Now, atomic mass, this is our last trend. Atomic mass is the simplest one. If we look at, this periodic table doesn't have it, but if you look at any periodic table whatsoever, you're going to notice the atomic mass tends to increase as the element gained protons. There are some rare exceptions to this, and this is actually the main reason I brought this up. Obviously, tends to get bigger as you go left to right, so atomic mass, just because you're adding more protons, and then of course it gets bigger as you go down. There are like 3 elements that actually tend to get smaller, and it's just because they need a different number of neutrons to stabilize, and neutrons are a bigger factor in mass than electrons. I believe iodine is one of the weird ones. Here, I can double check really quick actually, because it's worth knowing 1 or 2 of these, just so that you guys can look for it on your own or find it. So let's see. Yeah, so tellurium, which is element number 52, has an atomic mass of 127.6. Iodine, which is number 53, has 126.9. So it gets slightly smaller in atomic mass as the atomic number goes up. But in most other cases, it tends to consistently go up as you go over. I know there's 1 or 2 more examples where that's not the case. I don't remember exactly where to look for them, but I'm sure if you look at the periodic table for a while, you'll be able to find 1 or 2 of them. But in general, again, as you go left to right, it gets bigger, and as you go from the top to the bottom, it will also get bigger. So this is a summary of all the different trends that we're looking at. This adds in metallic and non-metallic character. We don't really care about that, but you should already know that these are where all the non-metals are, and these are all metals. So this kind of makes sense. The atomic radius, again, that gets smaller as we go down here. This arrow is backwards, actually, so I'm not sure what that's doing. Interesting. Ignore this one. This should be flipped. There, I redrew it. Ionization energy goes up As you go left to right, ionization energy goes up. As you go left to right, electronegativity goes up. Electronegativity, and then electron affinity. So this is basically the same thing as electronegativity. It's just a different word for it. And then let's see, what else did we talk about? Ionization energy, electronegativity. Oh, reactivity is towards the center. It gets lower, so it's going up. So we go like this. Shouldn't include the noble gases. So this is least reactive, and then there's a couple small ones. So that's our general summary of the trends. And that's really most of what we're going to be looking at with this unit. The rest of this unit, we have two different types of diagrams we're going to talk about at some point, but we will get to those in a little bit. Actually, that was the wrong. Yeah. So we will talk about electron dot models or Lewis dot models and Bohr diagrams. Bohr diagrams are kind of a pain, actually, because you have to draw out all of the electrons in an element. So this is the Bohr diagram for carbon. We'll get to that later, as well as the Lewis dot structure for carbon, which we will also get to later. And then that's going to be all the new content for this unit. So those of you that are gone, any assignments that I give, if you can do them at home, that's ideal. If you can't, then we'll make them up when you get back. I won't put them into any grade reports or anything like that. You guys have a lot of time before the semester ends, so I'm not too worried about getting you caught up. We will be having a test on this unit either at the, it won't be the end of this week. We won't be done quite in that time. So it'll probably be like Tuesday of next week. So those of you that'll be back, you'll have a chance to be able to take that quiz. Normally, if you stay caught up, if you need some extra time, then that'll be fine. We'll figure that out as well. But that's it for this one. Conferences are also at the end of this week, so if you have questions about that, just send me an email. If something's bothering you and you need help, or if you need to schedule a Zoom meeting with me sometime this week, go ahead and send me an email, and I will try to set that up with you as well.